And welcome back as we continue our cosmic journey. We are now going to dive into looking at galaxies. And let's go ahead and start by looking at the architecture of our very own. And in order to really get a good scope of our galaxy and how we came to understand how it works, we needed to do a little history and looking at the man named Herschel who actually first set about measuring the galaxy. In 1785, William Herschel made the first important discovery about the architecture of the Milky Way galaxy. Using a large reflecting telescope they built, William and his sister Caroline counted stars in different directions of the sky. They found that most of the stars they could see lay in a flattened structure encircling the sky, and that the numbers of stars were about the same in any direction around the structure. Herschel therefore concluded that the stellar system to which the Sun belongs has the shape of either a disk or a wheel. And this image kind of gives a rough diagram of what Herschel recorded. You'll notice that in this image, Herschel thought that the Sun was near the center of the disk. We now, though, know that Herschel was right about the shape of the system, though he was wrong about where the Sun lies within the disk. Interstellar dust absorbs light from stars, so Herschel could only see those stars within about 6,000 light years of the Sun. Today, we know this is a very small section of the entire 100,000 light-year diameter disk of stars that makes up our galaxy. And so when we start looking at our galaxy, one of the first features we are seeing are disks and halos. The brightest part of the galaxy consists of a thin, circular rotating disk of stars distributed across a region that's about 100,000 light-years in diameter and about 2,000 light-years thick. And of course, we can see that represented here in this image. We have, of course, this nice spiral, and we have, of course, this is the cross-section if you were to look at it from the side. Now, the very youngest stars and the dust and gas from which those stars form are typically within 100 light years of the plane of the Milky Way galaxy. Again, the plane is referring to this kind of cross-section area here. So you're not going to see as many as we move further away from that. Now, the mass of the interstellar matter is about 15% of the mass of the stars in this disk. Now, the stars, gas, and dust are not spread evenly throughout the disk, but are concentrated into a central bar and a series of spiral arms. Recent infrared observations have confirmed that the central bar is composed mostly of old yellow-red stars. The two main spiral arms appear to connect with the ends of the bar. They are highlighted by the blue light from young hot stars. We know that many other spiral galaxies that also have bar-shaped concentrations of stars in their central regions, and for that reason we refer to these as barred spirals. And so here we can see an example of these different types of galaxies. So image A shows a unbarred spiral galaxy. This is M74. It contains a central bulge of mostly yellow-red stars along with spiral arms that are highlighted with the blue light from young hot stars. But then when we look at image B, we can see a strongly barred spiral galaxy. You can see right here this kind of central region in NGC 1365. The bulge and the fainter bar both appear yellowish because the brightest stars in them are mostly old yellow and red giants. Two main spiral arms project from the ends of the bar. As in M74, these spiral arms are again populated with blue stars and red patches of glowing gas, hallmarks of recent star formation. Now, our thin disk of young stars, gas, and dust is embedded in a thicker but more diffuse disk of older stars. This thicker disk extends about 1,000 light years above and about 1,000 light years below the midplane of the thin disk and contains only about 5% as much mass as the thin disk. Now, the stars thin out with distance from the galactic plane and don't have a sharp edge. So approximately 2/3 of the stars in the thick disk are within the 1,000 light years of that midplane. Now, if we close into the galactic center, which is within about 10,000 light years, you'll see that the stars are no longer confined to the disk, but do form a kind of central bulge. When we observe with visible light, we can glimpse the stars in the bulge only in those rare directions where there happens to be relatively little interstellar dust. However, if we switch to infrared, we get a little bit different picture, as we can see here below, when we actually mapped the inner part of the Milky Way galaxy using infrared light. Now, in our galaxy, the thin and thick disk and the nuclear bulge are embedded in a spherical halo of very old, faint stars that extends to a distance of at least 150,000 light years from the galactic center. In that center, of course, is where most of the globular clusters are found within that halo. The mass of the Milky Way extends even further out, well beyond the boundary of the luminous stars, to a distance of about 200,000 light years from the center of the galaxy. This invisible mass has been given the name dark matter because it emits no light and cannot be seen with any telescope. Its composition is unknown, and it can be detected only because of its gravitational effects on the motions of luminous matter that we can't see. We know this extensive dark matter halo exists because of its effects on the orbits of distant star clusters and other dwarf galaxies that are associated with our own. One thing that helped enormously was the discovery that our galaxy is not unique in its characteristics. There are actually many other flat, spiral-shaped islands of stars, gas, and dust within the universe.